We will demonstrate a solid-state catalyst. We'll place a small amount of acetone in the bottom of a beaker. We'll heat a copper wire and suspend it from a stirring rod above the acetone. The copper catalyzes the oxidation of the acetone. The reaction is exothermic, which causes the catalyst to glow red hot. In a demonstration to show a solution catalyst, we will heat a solution of sodium-potassium tartrate. We will add a solution of hydrogen peroxide. The reaction is very slow initially, even at 60 degrees Celsius. We will then add some cobalt plus 2 ion. The cobalt ion forms a complex ion with the tartrate ion. The solution turns green due to the formation of this complex ion. The reaction becomes very rapid. We see the evolution of carbon dioxide gas. At the end of the reaction, the solution turns back to pink, showing the regeneration of the catalyst.
Welcome to this video, C.4.1, part of the Chemistry and Industry option. We are going to compare the modes of action, or in other words, sort of how these work, of homogeneous and heterogeneous catalysts. So catalysts are part of the core, and we're just going to extend this a little bit deeper to try and look at two different types and just sort of see how they work. So I'm going to do this as a sort of a chart where we compare the two different ones. So we're going to be able to draw a lot of connections because catalysts show up in the core and the environmental option a lot. So the Haber process, we already know, uses an iron catalyst. That's the one that produces ammonia from atmospheric nitrogen. The contact process, which is the one that produces SO3 for sulfuric acid. And catalytic converters, which are the ones that help reduce emissions from our cars. And hydrogenation, which is something in the organic unit, which if you haven't gotten there yet, you'll learn that later. And HDPE, which is a high density polyethylene. That's part of the options as well, and that uses a Ziegler-Natta catalyst. So that's one that you'll learn in more detail, but it's just good to start drawing some connections. So really in IB chemistry and a lot of industrial processes, we're using heterogeneous, and what that really means is that hetero means different, so different phases than the reactants. So if you're doing a reaction, the reactants are in a different state, like solid, liquid, or gas, than the catalyst, and the catalyst generally is solid, and then the reactants are generally gases in this case, but they could also potentially be liquids. Just jumping over to the homogeneous side, there's really not a whole lot of examples in terms of what we're learning in the core, but iodine clock reaction is one that comes up a lot. This is a homogeneous, and that's homogeneous because they're in the same phase. So in other words, this one is often liquid and liquid. So if you do an iodine clock reaction, that's happening in an aqueous solution, and that's usually solid in gases, or if it's not, it's liquid in liquid. So let's dig a little bit deeper and think about these solid catalysts. So here this metal sheet represents sort of a solid catalyst, and then these two spheres represent the reactants. So what happens here is the reactants are adsorbed. Now this is a key word that you shouldn't confuse with absorbed. Absorbed means it goes inside something. Adsorbed means it just sort of attaches to the surface, and then so it won't go inside. So the reactants are adsorbed onto the surface of the catalyst, and through interacting with that, it weakens the bonds within the molecule, and that will make them more likely to react. So in other words, if it weakens the bond, that means there's less energy needed to break the bond. So that means less activation energy. So in the core, we know that catalysts lower the activation energy. So this is how it does that, by weakening the bonds as it interacts with the reactants. And the surfaces that we make here, you can already see from the examples, you know, vanadium, iron, nickel, platinum, palladium. These are transition metals, and so these are often really good at being catalysts because they have multiple transition or multiple oxidation states, and so that ability to lose or to lose one electron and then be you know, sort of restored by gaining one, it's something that energetically is quite favorable, and can thus be used as a catalyst. Looking over at the homogeneous, this is what you would imagine is, you know, inside, if this was dissolved, this would be, you know, both in liquid state. So they'd be sort of just going around your reaction flask, and then they collide with each other. And so that's how they would interact with each other, through colliding, just through the random motion that they have through kinetic theory. So just to add on here, this is another way to visualize a catalyst, and what we're going to call active sites. So active sites are where the reaction actually happens. So in other words, where the reactants actually will sort of fit in your catalyst. So what you could represent that here is as in little dips. So if the reactants were to go over here, nothing would really happen. This is not an active site. But if they were to go into here, this is where they would interact with the catalyst in a successful way and produce a new product. So we want to have more of these active sites. More active sites will give you a more effective catalyst. Now, the availability of these active sites, so we're just, you know, if you're trying to imagine this, this is, you know, more likely what a heterogeneous, a solid transition metal one would look like. But the availability is going to depend on the type of catalyst you're using and the particle size. So maybe I'll just illustrate here. If any of you are taking biology, you'll be able to draw some connections here, because catalysts in biology are called enzymes, same thing. And so here you'd have an enzyme with these active sites that the reactant can attach to, and we call that the lock and key model. But that's just a model. If you're to try and visualize this enzyme, which is a protein, there's one part of this protein where a reaction can actually happen. So it can only really fit in one place. If this substrate here were to, you know, interact with this protein on any other part, there would be no, you know, change or no interaction that was creating a new product or a change. But as soon as it hits that active site here, it causes, in this case, you can see a change in the shape of the protein. So you can sort of think of that, you know, the size. If you have a larger size, it may be, you know, if it's a substrate, it may be more difficult for it to happen. But if you're defining the particle as, say, the enzyme, and the enzyme is large and has many active sites, then that can affect the availability. And the other part you can think about is whether or not it's clean of dust and other particles. So if there's some contamination here, then obviously the reactants couldn't actually adsorb to the surface. So that can be a problem if you get dust or particles in there. And the other part you can think of is whether or not, or how it was prepared prior to use. So for example, when we're using catalytic converters in cars, they only actually are functional after a certain temperature. And so you want to make sure that, okay, did you actually preheat or do something to make sure that this catalyst is, or that this active site will actually be able to carry out the reaction. So those are a few sort of different ways to think about the active sites and what affects them, but the key point is that the more active sites you have, the more effective your catalyst. In other words, the faster your reaction will be, because you can actually have more reactions going on at the same time.